it is better. I'm Sreejith from ICTS Pune, and I'll be telling you about the implementation and numerical testing of mean field approximation to certain n-body Hamiltonians in a specific context in quantum Hall physics. I'll start by giving a brief introduction. Quantum Hall effect, this is a quantum Hall trace. The diagonal looking line shows the Hall resistance, and with the distinct Hall plateaus. The squiggly line here shows the longitudinal resistance, which vanishes wherever the Hall resistance plateaus. The Hall resistance plateaus at certain specific rational fractions and rational filling fractions, and the fractions that occur between 0 and 1 are called the lowest Landau level fractional quantum Hall states, and the fractions that occur, 0 and 2, and the fractions that occur between 2 and 4 corresponds to second Landau level quantum Hall states. The quantum Hall states that occur in the lowest Landau level can be understood by using a model of single Landau levels, single energy level of electrons, together with the interactions between them. And this can be understood with a more effective picture using a theory of emergent particles called composite fermions. And one of the predictions of it is that the quantum Hall states occur at filling fractions with odd denominators. In particular, there is no fractional quantum Hall state at the filling fraction half. However, in the second Landau level, between filling fraction 2 and 4, there is a quantum Hall state at an even denominator, and it's a prominent one, and this corresponds to the longitudinal resistance at filling fraction 1/2 in the second Landau level. In general, there is no simple picture of what a simple description of general structure of quantum Hall states that occur in the second Landau level. However, the fractional quantum Hall effect that occur at filling fraction half is believed to be a P-wave superconductor of emergent particles called composite fermion. And it has the wave function that is similar to the helium wave function, helium superfluid wave function. This one. And the wave function is called the Pfaffian. The Pfaffian wave function, which occurs at the filling fraction half, is not particle Hall symmetric. The anti-Pfaffian, which is the particle Hall conjugate of the Pfaffian, also occurs at filling fraction half, and it has been shown that it's topologically different from the Pfaffian state. The two-body interaction, which should be stabilizing these states, is particle Hall symmetric in a single Landau level, and therefore, since there is a quantum Hall state there, it has to be described by either Pfaffian or anti-Pfaffian. At least that's the simple picture. So there has to be something that breaks the particle Hall symmetry. It was believed that the inter-Landau level scattering from higher Landau level is what what gives the symmetry breaking. This won't be discussed in this talk, but the actual or possible resolution of this might be a slightly more exotic, and these are results from very recent experiments and theoretical work. But I'll continue with some inferences from the previous conjecture. The effect of Landau level mixing can be studied by looking at scattering from higher Landau level intermediate states. This leads to correction to the two-body interaction Hamiltonian, the main Hamiltonian, the prominent part of the Hamiltonian, but that do not break the particle Hall symmetry, plus three-body interaction terms that actually break the particle Hall symmetry. Using this formalism, various kinds of numerical studies have been done. Some of the studies using exact diagonalization point to a Pfaffian as the actual ground state, and other studies using DMRG and other techniques show anti-Pfaffian as the ground state. However, they all point to the fact that the effect of particle Hall symmetry breaking is weak. So since the effect of Landau level mixing is the introduction of a three-body interaction, and it turns out to be weak, one can conjecture that the generic three-body interaction terms introduced by such scattering should effectively act as a particle-hole symmetric two-body interaction. Our own diffusion Monte Carlo calculation for this, this scattering shows that there is hardly any splitting between the energies of the Pfaffian and anti-Pfaffian state. The red dots show the energy of the Pfaffian state for various parameter values, and the blue dots show the energy of the anti-Pfaffian state, again for the corresponding parameter values. So with this conjecture, we wondered whether there is a mean field construction that will take the three-body interaction, which is particle-hole symmetry breaking, and if we can get a two-body interaction, which effectively reproduce the low energy spectrum of this three-body Hamiltonian. More precisely, we asked whether there is a mapping from the three-body Haldane pseudopotentials to two-body Haldane pseudopotentials. So what are Haldane pseudopotentials? The bulk physics of the quantum Hall system can be effectively studied using a model of the quantum Hall effect realized on a spherical geometry. In this geometry, the electrons reside on the surface of a sphere with a magnetic field generated by a monopole sitting at the center of the sphere. Translation and rotational symmetry of the planar geometry corresponds to full rotational symmetry of the spherical geometry. If you have a rotationally symmetric interaction term on the sphere, Wigner-Eckert theorem says that the energy of that interaction should depend only on the L-squared quantum number. For example, if you have a two-body interaction, the energy or the interaction should be a sum of two-body terms, and with the parameters VL, which corresponds to energy of states with fixed angular momentum quantum numbers L. And these parameters, these energies of states at fixed angular momentum are called the Haldane pseudopotential. Any rotationally symmetric Hamiltonian can be written using a few Haldane pseudopotentials. This corresponds to two-body interaction, but it can be generalized to cases with n-body interactions. To elaborate on our main point, the top panel shows the spectrum of a system at some filling fraction mu, and the bottom panel shows the spectrum at some filling fraction 1 minus mu. Each panel, the leftmost panel corresponds to a short-range three-body interaction, and the panels to the right corresponds to the spectrum of a Hamiltonian with generic terms added, which still keep the Hamiltonian somewhat short-range, but a three-body Hamiltonian which is more generic. The x-axis shows the momentum and y-axis is the energy. As you can see, for the shortest range three-body interaction, the spectrum at filling fraction mu is completely different from the spectrum at filling fraction minus mu. However, when you look at more generic quantum Hall states, more generic interactions, it turns out that the spectrum starts looking more and more similar to each other. So this motivates us to ask if there is a mapping to a particle-Hall symmetric interaction. A generic three-body interaction can be written in terms of matrix elements of the interactions in the second quantized language in this manner. And the simplest way to implement a mean field approximation is to replace correlation, some of the operators in this interaction term with the corresponding correlation values. For any gapped homogeneous fractional quantum Hall state, you can show that this correlation is equal to a delta function, a Kronecker delta function. For mappings of generic n-body interactions to n minus m body interaction, you can similarly replace some m-term, m-point correlation functions into its expectation value to get the n minus m particle interaction. With that replacement, you can make a mean field mapping of the three-body interaction to some two-body interaction with matrix elements that are given by a linear transformation of the original matrix elements of the three-body interaction. you can analyze this a little bit and show that this mean field mapping is a linear mapping. It is rotational symmetry preserving. That means that if the original three-body interaction is rotationally symmetric, the mean field two-body interaction is also rotationally symmetric. Somewhat more non-trivial is the fact that the mean field Hamiltonian that you obtain from the three-body interaction is exactly equal to particle-hole symmetrization of the three-body interaction. Now we tested the mean field mapping for specific cases, as you can see here. So all these spectra corresponds to various different finite size systems. The dots correspond to the mean field spectrum. The dashes correspond to the spectrum of the three-body interaction. And as you can see, and the numbers written here shows the overlap between the nearby situated states. As you can see, the lowest section of the energy eigenstates are almost exactly reproduced by the mean field approximation. And this is for another system size, filling fraction 3/5. To summarize, the various short-range n-body terms in the Hamiltonian are ways of specifying the constraints on the correlations in the many-body wave function. A generic n-body constraint, which contains many frustrated terms, effectively imply and are implied by constraints put on a smaller number of particles, and that is the reason why such a mean field approximation actually works. So with that idea, one should be able to construct fewer body terms for this n-body interaction, which reproduce the same low energy spectrum, which we have actually shown by constructing a mean field approximation. I have shown only the results for n equal to 3-body case, but can be generalized to 4-body and higher body terms. Okay.
I think one of the motivations that we are introducing the 3-body interaction was to see what effect does the particle-hole symmetry breaking does to the calculations. But now you're saying that in mean field theory that I mean it's preserved. So what was the point? That's my first question. Second question was that that you didn't consider disorder, right?
No.
Would disorder also not cause Landau level mixing and breakdown of particle-hole symmetry?
So I'll answer the easier question, the second one first. Disorder that has a slope, a gradient, which is much smaller than h cross omega, the cyclotron energy divided by the magnetic length, does not cause mixing. And that if there is strong disorder, there will be Landau level mixing. But it should not, well, anyway, we have not considered that kind of disorder, and we have not considered any disorder, in fact. That would cause some internal edge states. But generically for disorder disorder in an actual system, quantum Hall system comes from impurities that are located slightly far from the actual quantum Hall state. So the slope that occurs on the quantum Hall system is generally low. So that probably partly answers your question. The first question was, yeah, right. So as I said, the belief was that by introducing a generic 3-body interaction, you can break particle-hole symmetry. What we have shown is that that doesn't work. That is our result. So it is the Hilbert space is so constrained that putting a bunch of 3-body interaction just becomes equivalent to putting a constraint on the 2-body sector. So it doesn't really lead to a particle-hole symmetry breaking. To answer so what is the actual resolution of the question of what the state is at that filling fraction? It turns out that it has to involve disorder. So there are 2 kinds of states that are possible at that filling fraction, Pfaffian and Anti-pfaffian. And these are pinned down by disorder in the system. And the actual quantum Hall state that occurs at that filling fraction is described by some quantum percolation model that involves Pfaffian and anti-Pfaffian. Short answer is that three-body interaction does not break the particle-Hall symmetry, generic three-body interaction. If you fine-tune the three-body interaction, it does break particle-Hall symmetry. And the resolution to the original problem is somewhat more complicated.
Any other question? Okay, so let's thank Sreejith for the talk.